Today we expect to be able to connect an induction motor to a source of AC and it will start. We don't have to worry about whether the system can supply the current it will draw. We just choose a starter from a catalog and connect it up. But it wasn't always that way. Up until about 1940, it was common for induction motors, both squirrel cage and wound rotor, to use some form of reduced voltage starting. Since this was also the case with direct current motors the induction motor was intended to replace, this wasn't seen as a serious issue at that time. The motor in the patents that Westinghouse purchased from Tesla required various modifications before a working induction motor could be put into production. One of the most serious issues was that Tesla's patents employed salient poles. While this was the winding typically used on DC motors in the late 19th century, at Westinghouse it was soon realized that the harmonics these poles produced caused serious problems. The use of distributed windings was the solution. The first induction motor with distributed windings was tested in 1892. In modern times, we've come to view the term induction motor as referring to a squirrel cage motor. However, the early induction motors had distributed windings on both primary and secondary. There was no squirrel cage motor. The secondary was brought out to a set of collector rings so that the various resistor values could be inserted into the circuit during starting. This was the normal method of operating an induction motor because the windings themselves offered very little resistance to current flow. During testing, the motor performed better than expected, so it was suggested that the secondary be short-circuited by exposing the bare copper, and the ends were then thoroughly soldered together, making a continuous ring of metal at each end. Test results proved that this type of secondary was effective when starting conditions would permit. In our modern world, the phrase, where starting conditions would permit, must seem like a strange qualifier. In the 1890s, there were no interconnected power systems. The alternators were most often driven by steam engine, and as such, their ability to deliver clean electrical power was very dependent on the prime mover's ability to follow the load demands. Most induction motors were powered by a local grouping of one or two alternators. At the turn of the 20th century, several large power stations were coming into operation. The idea of connecting one station to another was theoretically intimidating, the theory behind it only just being developed by the best minds in the profession. Steinmetz' phasor concept was new and would take several years to come into general use. As late as the 1930s, when several stations over large geographical areas were interconnected, the high starting current of the across-the-line start squirrel cage induction motor prohibited its general use. This can only be attributed to the fact that the distribution systems inside the factories were not designed to serve this sort of load. Because numerical analysis of electric circuits was not well developed at that time, Lamy graphically determined that if the secondary resistance could be increased during starting, then good pull-out torque and starting torques could be obtained with workable slips approaching constant speed. Constant speed was important since production output was based on the expectation of the same constant speed as a direct current motor produced. Tests confirmed that this type of motor could produce a reasonable amount of torque using cage-type windings. Production began soon afterwards. Although these induction motors developed acceptable starting, full load, and pull-out torque, this high torque came at a high starting current of 6 to 9 times full load. Because of power system limitations, a voltage-reducing starter was typically used on these motors. Once up to speed, the motor would be connected directly to line voltage. This new motor was called a Type B and was available in sizes up to 300 horsepower in both 25 and 60 hertz. It was manufactured up to the year 1897. Westinghouse realized that it was possible to design a squirrel cage induction motor where there was no need to connect the secondary to resistors. Any voltage reduction that was needed could be provided in the primary supply. Up to this point in time, Westinghouse had the stator as a secondary, but they changed their configuration to be the same as that of General Electric, where the cage winding was a secondary and the stator would be the primary. These motors with rotating secondaries would be known as Type C. Several modifications included the use of improved conductor insulation, double-end ventilation, and a heavy frame with cast feet. Cooling air was drawn in through large openings in each end bracket and discharged through the stator core. By 1910, there would be several subclasses. Realizing the cage resistance played a significant role in the motor's attributes, various forms of cage construction were attempted. It was found that by employing different amounts of resistance in the secondary, different torque, current, and speed conditions would result. Initially, a simple bolted construction was used to attach the secondary bars to the end rings. End rings made of iron and various bronze and brasses were used to modify the resistance of the cage. The Type C motor had acquired a reputation for sturdiness and reliability, but the efficiency was low and the power factor was less than satisfactory. One reason for this was the use of open slots, making the motor's magnetic efficiency less than desirable. During the first decade of the 20th century, as a result of serious competition from other manufacturers, Westinghouse realized that the Type C motor would have to be upgraded. The first attempt was to be known as the Type CC motor, but before it could be sent to market, it became apparent that a somewhat lighter and smaller machine was desirable. As a result, another upgrade was made. This was called the Type CCL motor. The most significant change from the Type CC was its increase in efficiency and improved power factor. By the early 1910s, squirrel cage induction motors were becoming accepted as a viable substitute for a DC shunt motor. Beginning in 1920, the Type CS motor was developed. It had a die-cast aluminum rotor cage with copper bars and end rings. Production of the motor continued into the 1930s. Some issues needed correction. The wide open motor enclosure, for instance, had no protection against dripping liquids or solid particles. By 1930, the motor had a NEMA rating. The National Electrical Manufacturers Association had standardized the basic mounting dimensions for integral horsepower motors and assigned standardized horsepower ratings to these frame sizes. The motor was end ventilated with cooling air drawn in one end bracket, passing axially through the frame and discharged at the opposite end. In the 1940s, the open drip-proof motor came on the market. Its housing offered substantial protection to the internal parts. Sleeve bearings were supplanted by ball bearings. The motor was single-end ventilated, with cooling air drawn in one end bracket, passed axially through the frame, and then discharged at the opposite end. In 1950, the U-frame motor was introduced. It had enhanced drip-proof protection, was double-end ventilated, and provided with improved high-temperature insulation. Only minor improvements, largely in the area of insulation materials, have occurred since this point in time. At the beginning of the 1930s, the induction motor industry had new business of approximately 40 million US dollars. In 2021 terms, this is approximately $600 million. The induction motor had become the motor of choice for general use drives. These applications covered a wide range from washing machine motors of a sixth of a horsepower to motors driving large warships rated at more than 20,000 horsepower each. The current taken by squirrel cage motors of less than 50 horsepower when starting was improved, but since it was still more than 6 times full load, many power companies restricted its use. The largest induction motors were not squirrel cage motors, they were wound rotor induction motors. Motors over 50 horsepower were required to use reduced voltage starting. This was a serious problem. Nearly 40 years after Tesla sold his patents to Westinghouse, inrush current was still restricting the widespread use of the squirrel cage induction motor. The race was on to see who could develop a squirrel cage induction motor that the power companies would be happy with. There are 2 classes of squirrel cage involved based on how the inrush current would be controlled. One class depended on the mechanical effects of centrifugal force, while the other used inductive means related to the skin effect to vary the rotor bar impedance. An example of the mechanical type was the Morelli motor. This motor used springs to switch the rotor resistance and limit the rotor current. The figure shows cage bars that have a resistor ring mounted to the ends of each rotor bar. This provides high rotor resistance during starting, resulting in high torque. As the motor came up to speed, sheets of copper attached to springs were forced outward towards the resistor ring. At a point in time when the rotor inrush current had been reduced to an acceptable value, the copper sheets touched the resistor tips and shorted them out, removing the starter resistance from the rotor. The principal disadvantage of this motor, aside from the obvious mechanical difficulties, was the fact that the heating due to the resistance losses in the end ring added to the heat load on the motor. Burnout might occur if starting time was unduly prolonged. Much more work was required to bring the induction motor to the point where it is today, the go-to motor for more than 90% of the world's motor applications. The most successful method of inrush current control is by means of changes in the rotor bar impedance. In the early writing, there is frequent reference to the deep bar effect. An explanation of how this works generally involves either advanced mathematics or an appeal to the supernatural. We'll take the latter approach and begin by describing sine waves. Commercial current is in the form of a sine wave. Why it takes the form of a sine wave is a bit deeper than we're going to go here. Those who are interested can read about it in the text Electrical Machinery, Transformers and Controls mentioned at the end of this video. When the current is maximum at the top of the sine curve, so is the magnetic field intensity that the current produces. In other words, the lines of magnetic force are densest at this point. But notice that this is the point where the intensity is not changing. It's like a roller coaster car coming to the top of a hill and just barely stopping for a brief second until the drive chain catches up to it and it starts to move again. In order to induce voltage in a conductor, the field must be changing. So at this point, no voltage is induced in the conductor, a rotor conductor in our case. As time progresses and the current sine curve crosses the timeline, the current and the lines of force that the current produces are changing at the greatest rate. Keep in mind that the current and the magnetic field that it produces are in phase with each other, so this is also the point where the magnetic field is changing at the greatest rate. Since it's the rate at which these lines of magnetic force are changing that induces voltage in a conductor, we have zero voltage generating when the current is maximum, and maximum voltage generated when the current is zero. This is what is meant when we say that the current is 90 degrees out of phase with the voltage, or what is the same thing, the voltage is 90 degrees out of phase with the current. So we have the situation where a supply voltage causes a lagging current in the stator of the motor. This lagging current in turn induces a lagging voltage in the rotor. This lagging rotor voltage causes a lagging current in the rotor. This means that the stator current and the rotor current are 180 degrees out of phase with each other. And so are their respective magnetic fields. Therefore, the magnetic fields associated with each of these currents are in opposite directions. This results in zero torque applied to the motor's rotor. This may be easier to visualize in terms of flux vectors. The stator of an induction motor carries three-phase alternating current and is wound in such a way that this current produces a magnetic field that rotates. This rotating magnetic field sweeps across the rotor and induces an alternating voltage in the rotor's conductor bars. In an inductive circuit like the rotor and stator of an induction motor, current lags the voltage. As such, the two magnetic fields oppose each other and no torque is produced. In order to produce torque, the impedance of the rotor must become more resistive, bringing the rotor flux nearer to a 90-degree angle with the stator flux. To accomplish this, the impedance of the rotor must become more resistive. To understand how this can happen, we'll begin by looking at what is known as the skin effect. Shown here is a circle that represents a cross-section of a conductor. Below it is a graph of a sine wave. There is no current flowing at time zero. As time progresses, the magnetic field produced by the current increases and expands in ever-increasing circles. Keep in mind that these circles are fictitious concepts, conjured up to help us understand the effects of magnetism, whatever that is. As the current increases, so does the field intensity, each circle getting larger and being replaced by one behind it. Then, as the sine function begins to decrease, the reverse happens. The circles grow smaller, and the cycle repeats. Until the current and its flux reach zero. And again, the cycle repeats. What we see here is that, except for a brief instant when the flux is zero, there was always magnetic flux changing near the center of the conductor. As one circle of magnetism expands, another appears to replace it. So, except for the infinitesimal instance when there is zero magnetism present, there is always magnetic flux at the center. As you go out from the center, the flux is less and less. The closer to the center, the greater the impedance. The inductive reactance is greater closer to the center, and so the impedance is higher there. Current flow will be greater in the areas of less impedance, toward the outer portions of the conductor. This is what is called the skin effect. We can use the skin effect to control the resistance of the rotor conductors. There are two reasons to want to control the rotor resistance: torque development and the control of inrush current. Here we see a section of a deep bar rotor conductor similar to that used circa 1910. These conductor bars are usually made of copper alloy and surrounded by magnetic steel. At the top is located the air gap that separates the stator from the rotor. When power is first applied to the motor, the frequency in the stator circuit is the system frequency, either 60 or 50 Hz depending upon the system. At standstill, this is also the frequency in the rotor circuit. It may help to understand that the stator and rotor are two isolated electric circuits coupled to each other by magnetism. The induction motor may be considered to be a transformer with a variable turns ratio. As the rotor starts to move, its rotational speed increases and begins to approach the speed of a rotating magnetic field. As a result, the rotor sees a lowering frequency. This lower frequency produces a lowered voltage in the rotor that affects both the current and the impedance of the rotor circuit in a complex way. At rated speed, the rotor circuit is operating near the frequency of the stator's rotating magnetic field, only a few cycles per second. But it's not just the rotor voltage that changes, the rotor impedance changes as well. This is because the reactance part of the impedance is determined by the frequency the rotor sees. The torque produced by an induction motor is governed by the way the rotor impedance changes. The impedance changes are largely a result of the shape of the rotor bars. A quantitative explanation requires some serious math, so a simplified explanation will have to suffice. Because there is much less magnetic steel in the air gap, the field is weaker there. The inductive reactance, the AC resistance to current flow, is greater at the bottom of the slot because the magnetic lines of force are denser there. When the motor is first connected, the rotor frequency and hence the reactance will be the greatest. So, as the motor comes up to speed, the reactance of the rotor bar will change and so will the apparent resistance. Let's have a closer look at what happens with a simple deep slot rotor bar when the rotor is at standstill. Here we see the entire bar has equal conductivity. However, when the motor is connected to the line, the rotor sees the line frequency. As a result, the skin effect is maximum and the rotor slot has a high reactance towards the bottom of the slot. Current will tend to flow in a reduced area toward the top of the bar, resulting in high resistance. A high resistance is what we need in order to increase starting torque. The more resistance the rotor circuit has, the closer its magnetic field will come to that of the stator, and the greater will be the motor's torque. The way the motor comes up to operating speed can be determined by the shape of the rotor bars. We've seen that the reactance of a deep bar provides high starting torque, and that as the frequency in the rotor decreases, so does the bar's resistance, and so does its torque. For a short bar rotor, the skin effect is less pronounced. However, in this case, resistance is higher because the amount of copper is less. The effect of this resistance is to produce a motor whose torque increases throughout most of the speed range. The deep bar rotor produces what the National Electrical Manufacturing Association refers to as a Class A torque speed characteristic. Class A motors are suitable for applications requiring high starting torque. The short bar rotor is NEMA Class D. They're used for machinery with high peak loads such as elevators, hoists, and punch presses. NEMA Class B and C characteristics are produced by various bar configurations used to accentuate certain aspects. Class B is the most common design, suitable for most applications of pumps, fans, and other situations that don't require the specially high starting torque that Class A is capable of providing. Stan Rogers, White Collar Hauler.
Well, I rise up every morning at 7:45. Some woman who's my wife tells me not to be late. I kiss the kids goodbye, I can't remember their names. And week after week, it's always the same. And it's, oh boys, can't you code it? Whoop, and program it right. Nothing ever happens in this life of mine. I'm hauling out the data on the Xerox line. And it's code in the day to give the keyboard a punch. Then cross, correlate, and a break for some lunch. Correlate, tabulate, process, and screen. Program, print out, regress to the mean. And it's, oh boys, can't you code it? Whoop, and program it right. Nothing ever happens in this life of mine. I'm hauling out the data on the Xerox line. Yeah, then it's home again, eat again, watch some TV, make love to my woman at 10:53. I dream the same dream when I'm sleeping at night. I'm soaring over hills like an eagle in flight. And it's, oh boys, can't you code it? And program it right. Nothing ever happens in this life of mine. I'm hauling up the data on the Xerox line. Someday I'm gonna give up all the buttons and things. I'll punch that time clock till it can't ring. Burn up my necktie and set myself free. 'Cause no one's gonna fold, bend, or mutilate me. And it's, oh boys, can't you code it? Ooh, and program it right. Nothing ever happens in this life of mine. I'm hauling up the data on the Xerox line. And it's, oh boys, can't you code it? And program it right. Nothing ever happens in this life of mine.